Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 17, 2025, about 2 days ago. The standout result is a teacher-student setup where a force-sensing robot arm safely guides a humanoid to learn in the real world, doubling zero-shot walking speed in about 20 minutes and enabling a swing-up skill from scratch in about 15. The paper is titled, Robot Trains Robot, Automatic Real-World Policy Adaptation and Learning for Humanoids, and as we will see later, the practical gains are striking. In short, the system marries safety, richer real-world rewards, and efficient sim to real adaptation using a dynamics-encoded latent vector. Building on that, 2 posts frame the system as parent-style guidance for real-world motor learning, highlight safe hardware and algorithm design, and point to efficient humanoid training with moderate engagement. Also, the authors shared their code on GitHub. You'll find the official implementation with a README, setup steps using Conda and Mamba, folders like docs, examples, launch, motion, scripts, and toddlerbot, plus a fine-tuned config. It includes pre-training and real-world training walkthroughs, hardware setup for UR5 and FT sensor, and a pre-trained checkpoint reference. Alright, this figure sets the scene. A robot arm acts as the teacher while the small humanoid on a treadmill is the student. The green panel lists what the teacher provides: safe exploration, a staged learning curriculum, informative reward from force sensing, deliberate perturbations, failure detection, automatic resets, and compliant control. The red panel highlights the student goals: real-world learning and sim to real adaptation. Together, the setup enables long, unattended training with protection and rich feedback. Continuing with the setup, this diagram maps how the teacher gear connects to the student loop. The top block groups the robot arm, the force torque sensor, the mini PC, and the optional treadmill, while the lower block shows the humanoid and the training workstation. The arrows encode roles. Teal lines carry measurements like force torque and inertial readings. Orange lines issue control like admittance and treadmill speed. Green lines send real-world transitions, and red lines return the latest policy for deployment. Now, this diagram walks through the 3-stage adaptation. At the top, many randomized simulations feed physical parameters into an encoder that produces a dynamics latent, which modulates the actor through feature-wise linear modulation, while the critic and actor train together. Moving down, the policy freezes and a single universal latent is optimized across sims. Finally, on real hardware, only the latent continues to learn while a fresh critic trains, giving safe, data-efficient tuning without changing the actor weights. Next, this table compares walking stability across several adaptation choices at a fixed treadmill speed. Focus on the body angles and contact forces. Lower numbers mean steadier gait and gentler interactions. The teacher-student method delivers the best trio overall, with the smallest torso roll and pitch, and notably reduced end effector forces along X, Y, and Z. Baselines that freeze the policy or hold the dynamics latent constant show higher forces or larger tilts, indicating less stable transfer and weaker real-world fine-tuning. Okay, this swing-up ablation figure has 3 parts. First, the left panels show the suspended humanoid driven by the arm, illustrating the X and Y compliant axes. Next, the center plot charts reward versus steps, where helping rises fastest and ends highest, while fixed and perturbing trails behind, and removing the pre-trained critic lowers performance. Finally, the right bars depict the schedules: fix only, help in the middle, or perturb in the middle, with fixed phases at the start and end. Building on that, 2 takeaways stand out. First, a force-aware teacher arm unlocks safe, unattended, real-world learning with meaningful rewards and automatic resets. Second, tuning a single dynamics latent through feature-wise, linear modulation gives fast, stable sim to real adaptation. Feature-wise, linear modulation means conditioning the policy by scaling internal features. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.